Welcome, everyone. This is the last morning session of our virtual workshop. And this is a session with four talks covering nickelates and also cuprates. The first talk will be given by Harrison LaBollita from Flatiron Institute. And he will tell us about from square planar to octahedral nickelates in the electronic structure perspective. So it's all yours, Harrison.
Okay, yeah. Well, good morning, everyone. Good afternoon, good evening from wherever you are in the world. First, let me start by thanking the organizers for the opportunity to speak at this workshop. I've very much enjoyed getting to hear about all the updates happening in this field of unconventional superconductivity. Um, so, what I would like to try to do today is offer some perspective on the electronic structure of both the square planar and octahedral nickelates that we've been talking about over the past couple of days. And so let me start by putting this in the broader context, at least that I started working in this field, which is this question of can we make a nickel oxide that is a proxy for the physics of the cuprates? And so in practice, what that means is can I find a material of interest, say a nickelate, that has some resemblance to and manifest a lot of the characteristics that we think of when we think of the cuprates. So nominally some kind of two-dimensional square lattice made of some transition metal and oxygen. I would like to put that transition metal in some D9 electron configuration to be isoelectronic to say copper 2 plus. I'd like those transition metals to hybridize strongly with the neighboring oxygen to give rise to some kind of strong magnetic antiferromagnetic fluctuations. And if I weren't able to do all that, do I actually get cuprate phenomenology, mainly this diagram of magnetic insulating state that is neighbored to some dome of superconductivity. And so, as we all know, that was more or less achieved by the Stanford group with their realization of superconductivity in this so-called infinite layer nickelate, which realizes a lot of those features. I have two-dimensional square planes of nickel oxygen. Um, if I do the valence counting, I have monovalent nickel, which is D9. And if I do map out the phase diagram, I see something that's reminiscent of the cuprates. I have some kind of upturn at low T that then turns into a wide superconducting dome, and then something that looks more or less like a Fermi liquid metal in the overdope side. So I think now the question is really, what are these features that we were kind of interested in having were actually relevant for the superconductivity in the nickelates? And so it's in that context that I sort of want to set the stage for this talk. Um, and so, as we all know, there are now two families of nickelates, and I'm sort of stealing the cartoon from Barrett on Monday because I liked it so much that sort of characterizes so perfectly where we're at. These two families are built out of more or less the same building block. I take some perovskite and I stack it in some interesting way, and then do some interesting chemistry and remove the apical oxygens. And then I dope that thing and I get some dome of superconductivity with a TC on the low end of 10 Kelvin, but in recent experiments have reached as high as 40K. And that gives me the square planar nickelates, which are nominally a D9 electron configuration. And then on the right, I can go to the octahedral or the Ruddleston-Popper nickelates. And again, I take this perovskite building block, I stack it with some in layers of that thing. I put rock salt layers in between. And if I start squeezing that or applying pressure in a pressurized way or applying some compressive strain, I also get superconductivity with TCs of anywhere from 30 in the case of the tri-layer all the way up to some recent reports of 90 Kelvin in the bilayer. And so I think sort of the broad question that we can ask ourselves about these two families of nickelates is what is the link, if any, between these two families, and do they have some sort of underlying similarities with regards to their the nature of the superconductivity? Okay, so that sets the stage with the background that I want to tell you about sort of the cast of characters in these two families of nickelates. So we have the square planar ones, which are nominally in this D9 electron configuration. And then we have the octahedral nickelates, which are something like D7 plus delta. So let me start by saying a few things about the square planars. And this is really my entree into the field. So we knew about Harold's work and that you could dope the infinite layer and see superconductivity. But we also knew about these line phases, these so-called reduced Brottleston poppers, which have this general chemical formula of rare earth, nickel, oxygen 2. And here the lowercase n I'm using to refer to the number of nickel oxygen 2 planes. And as has already been discussed in this workshop, um, an interesting feature of this family is that the nominal valence that you write down is a function of the number of nickel oxygen 2 planes. So naively, one might say, well, if I can control the valence or the nominal filling of the nickel, perhaps I can traverse the cuprate phase diagram, not with chemical doping, but say layer dimensionality. And so if you naively do that and write down the valence for, say, the 4, 5, and 6 layers, you see that they fall more or less directly in the dome of in the cuprate superconducting dome. So one could ask, if I could grow this material, would it be a superconductor? And so that was really the motivation for looking at the electronic structure of this series of materials, which is what Antia and I did back in the day. And basically, we just did a few band structure calculations, which I'll tell you more about in a minute, to extract trends. And from those trends, we just pointed out a few key things that we thought might be relevant for superconductivity, and we made the prediction that perhaps indeed these sort of line phases of multi-layer square planar nickelates would be good candidates for superconductivity. And so this is, leads naturally into really the heroic work of Julia's group, which is actually growing this material. They grew here the 5-layer nickelate, which again is more or less an optimal doping in the cuprate phase diagram. And they find that it turns from something that looks like a metal into a superconductor. So it's kind of a remarkable discovery that with this sort of simple line of thinking, you actually find superconductivity. But of course, it'd be great if we could get the whole series, right? It would be nice if we could see what happens as a function of the number of nickel oxygen 2 planes. And so again, this is the heroic work and sort of emphasizes how talented all the crystal growers are in our community to realize sort of these very difficult materials. So here is the phase diagram. Now, instead of a function of chemical doping, a number of nickel oxygen 2 planes. And you can see that if I start in the tri-layer guy, which is on the far right of the phase diagram, I get something that looks like a metal. But as I start adding layers, moving my formal valence into the superconducting dome, we see superconductivity turn on at around 4 layers with this dome. And then superconductivity turns off somewhere between 8 and 10. And so this is kind of remarkable. So now let me just comment a bit about sort of the gross electronic structure features of these multi-layer square planar nickelates. So when you do a band structure calculation, you find the following things. You see that they're in dx squared minus y squared bands, 1 for each nickel oxygen 2 plane. And here I'm showing the 5-layer as an example, and with the x squared minus y squared character shown in orange. But you can also see you get these rare earth 5D states, you get these extra states shown in purple. Those guys come from the hybridized rare earth with the nickel 3z squared minus r squared. And if you watch what happens as a function of n, this hybridization is actually increasing. So it's strongest in the case of the infinite layer, but weakens as I go, as I reduce the number of layers, and completely disappears in the tri-layer case. You can do the same game and ask what's happening with the oxygen. So it turns out that in the infinite layer guy, there's sort of a very much a lack of hybridization between the oxygen and the nickel. But as I start decreasing the number of layers, the oxygen states start to participate around the Fermi level, and you can see the increased amount of hybridization. And so you might think, I'm going from something like a Mott Hubbard type limit in the infinite layer, but as I reduce the layers, I'm going towards, say, a charge transfer limit, if we want to use that language. Um, one might say more cuprate-like. And then I'll just also comment that because of these multi-layers are sort of in nickel oxygen 2 planes sandwiched in between some spacer layer, they're much more two-dimensional in terms of electronically. So if you look at the fermiology, it's much more two-dimensional compared to, say, the infinite layer, which doesn't have this sort of spacer layer that breaks the c-axis symmetry. And so that's just one interesting contrast between the infinite layer nickelates and these multi-layer square planars. And so I want to highlight some recent work that we've done. So of course, we've looked at all of that, and the gross features match, say, X-ray absorption and map onto RICS data. But it would be nice if we could actually measure the dispersion. And so being in thin film geometry, you can imagine that that limits some of the techniques available to us to do that. But what I like about this recent effort in collaboration with Gail is that we kind of did that implicitly by measuring the Seebeck. And so you can think of the Seebeck as some way to measure the average dispersion through the sample and really looking at the particle hole asymmetry between my bands. And what we find is that if you take the appropriate limit, that the Seebeck is actually just a function of the band structure. And taking some tight binding fit to the band structure that you would get from DFT, you can actually reproduce both sign and magnitude of this. So I think this is a nice confirmation that we more or less have the right idea of what the basic electronic dispersions look like in these multi-layer nickelates. And so I wanted to bring up transport just to make the following aside. I've been thinking about transport in metals for a lot recently, and I want to advertise a bit of recent work. So transport is notoriously difficult to calculate for a couple of reasons. One is you need very accurate integration of the Brion zone, and you need a very accurate self-energy at low frequency. And through recent developments with a team at the Flatiron, I think we have more or less numerical control on both of these things. And what this is really going to do is put quantitative predictions of transport and sort of correlated materials on the table, which I think is an exciting, stringent test of our understanding of the materials that we're interested in. Here's an example looking at strontium vanadate. And you can see we're actually computing resistivity versus temperature. And from the calculation, we actually find very beautiful agreement with some of the data that's on the highest crystalline samples. So I really think that this is really pushing the boundary of what we can do with numerics, and is quite exciting to put a new sort of experimental theoretical test on the table. So let me just summarize what I wanted to say about the square planar nickelates here. Of course, everything I've told you is basic DFT electronic structure opinion of these materials. But of course, what we'd probably like to do is build some mini body theory on top of that. And I think when you do that, there's more or less sort of three camps throughout the literature. And I'm just putting this here to summarize what they are and show that there's, that this is not a concluded problem, and that there's a nice healthy debate amongst all of us working on this of the different camps. So one of them being that this is sort of a cuprate-like scenario driven by this x squared minus y squared orbital. A competing vision would be multi-orbital physics, sort of this Mott-Hun's-like picture. And then another picture is I actually have a Kondo-like scenario where I have local moments on the x squared minus y squared that are screened by the rare earth states. Okay, so that's what I wanted to say on the square planars. Now I want to switch gears and tell you a couple of things about the octahedral nickelates. And I've divided them up into two camps. We have these sort of conventionally stacked Ruddleston poppers, and in these sort of polymorphs or hybrid stacked materials. So the conventional is naturally what you think, just taking in layers of perovskite and stacking them along the c-axis, whereas these hybrids are sort of alternating two different ends and taking, in the case of the ones I'm showing here, this is alternating the single layer with the bilayer or the single layer with the trilayer. Okay, so let's look at the sort of electronic structure from a naive picture of the conventional Rutherford Popper nickelates. So here I'm no longer in this D9 limit, but I'm now towards D7. And I can think if I just take in layers of these things and hybridize them together, I'll get a bunch of anti-bonding and bonding states. And so here, if we look in the out of plane direction, the bonding anti-bonding splitting is strong. So I have these sort of flatter z squared minus r squared bands. And then I put the x squared minus y squared orbitals somewhere between. And when we look at the DFT calculation, we more or less see these flat x squared minus y, or flat z squared bands showing in green with both bonding and anti-bonding combinations. And then these dispersive x squared minus r squared, y squared bands. Going to the tri-layer, I now introduce another layer degree of freedom. So now I have bonding, non-bonding, and anti-bonding combinations. And I think one interesting thing that I want to point out that I quite like is that you can see that the different layers contribute to these states differently. So I'm projecting onto the inner layer in the top plot, and you can see it only contributes to the bonding and anti-bonding combinations of these 3z squared minus r squared. Whereas the outer two planes contribute to all three states. And so what I think this highlights is an interesting layer differentiation in the tri-layer where the outer planes are really somewhat different than the inner plane. And I think it's in that context that we can start to understand some of the experiments, whether that's on the density wave or the recent work that we've been a part looking at terahertz. And I think that sort of the big question that we're all asking ourselves is, okay, how do I, what do I do with these low energy electronic states? How do I get a density wave, or how do I get superconductivity? And we're trying to reconcile the relevant roles of these, basically these two orbitals, if you will. Let me just briefly comment about the hybrids, these sort of hybrid stack Rutherford poppers. So as I tried to allude at the beginning, in the hybrids, we're just taking two stacks, one with different numbers of layer and alternating them along the c-axis. And what I find interesting about these materials is that they really look like an electronic superposition of the two materials. So in the case of the 1313, I'm adding, say, single layer perovskite with tri-layer. And in the band structure calculation, what I'm trying to do is project onto the different layers. So here, the orange are the states coming from the single layer, and the blue are states from the tri-layer. And you can see it really looks like the sum of these two band structures. And this holds for also if I look at this so-called 1-2-1-2, where I'm taking the bilayer and sort of interleaving this single layer in between. So I find that kind of fascinating how nature does that. Okay, so now what we would really like to do is take that basic electronic structure theory and build some mini body perspective on top of that. Naively, we think interactions are important, and so we would like to understand how those change the picture. So here I plot the fermiology of all of these octahedral nickelates that we've talked about so far at the DFT level. And if you recall, the DFT dispersions for the x squared minus y squared bands were quite dispersive, while the z squared bands were quite flat. So you could imagine that, okay, probably the x squared minus y squared bands are probably more or less okay. They're very dispersive. They might have some mass renormalization, but the flatter z squared bands might be more amenable to some kind of electron correlation effect or some interaction effect. And maybe DFT's opinion of where those states are needs to be shifted around. So one way of doing that is taking the DFT band structure and using some kind of quantum embedding method where I treat, say, some subset of those states with some many-body method. For example, dynamical mean field theory. So in that context, I would take the nickel states and treat them as some many-body problem that I solve and get some self-energy, and embed that back into the crystal. And so if I do that, then I get something that looks like this. And I want to just walk through how the fermiology changes. If I look at the conventional layers, um, more or less the dispersions remain the same. There's some broadening due to some lifetime effects, but more or less everybody stayed the same. And what I find interesting about this is that we see this additional orthorhombically distorted pocket at the zone center, which doesn't seem to show up in the ARPEs. In the case of the hybrids, as I was telling you, we're stacking these single layers interleaved with either bilayers or trilayers. And one might think, if you know anything about the 214 nickelates, that that guy is nominally D8, and so therefore it's some high spin, half filled, close to a insulating regime. And when you do the calculation in this way, that sort of pops out. And so when you go to this naively higher level of theory, you remove the states coming from that single layer, and you're only left with in the case of the 1-2-1-2, the bilayer contribution to the fermiology, or in the case of the 1-3-1-3, this trilayer. So I find this all, very compelling and quite interesting. But I want to just conclude with the discussion and take off my speaker hat and put on my salesman hat. So what we're quite excited about in the Flatiron is this recent effort to sort of upgrade all of our electronic structure tooling. For those of you that are familiar with these quantum embedding techniques, you know that combining density functional theory with some dynamical mean field theory has always been an awkward thing to do. There's some inconsistencies within the theories that make combining them a bit difficult. And this was pointed out more than 20 years ago. And the better way to do it is, say, use a better theory than, say, density functional theory. And so the natural choice for that is to go to many body perturbation theory, or GW. But as you know, this has been historically really challenging to do in in a realistic materials context. So what I'm advertising, or what I'm trying to say, is that through recent effort at the Flatiron, we've more or less solved that issue. And now GW in a realistic context is not easy to do, but can be done in a very efficient way. And we can actually combine that with our many body theories. And so the reason I wanted to put all this in is advertise that I really think we're going to enter a new paradigm for electronic structure research. And I think this will be an excellent new tool to apply to all of the materials that we're interested in. And I hope shed new light on and provide new insights into these materials. And so with that, let me just thank all the amazing collaborators that I've had the opportunity to work with and learn from over the past years, and just conclude the talk. And thank you for your attention.
Thank you very much. That's a very nice talk. Floor is open for questions. Can I maybe, before folks have any questions? So a quick question about your transport calculation method. Can you say a bit more about what kind of correlation effects uh, can be included in this kind of calculation?
Well, I mean, in principle, any, but here we're kind of limited to local correlations, at least at within a DMFT type approximation. So here I'm putting in a sigma of omega and temperature, but of course, going beyond this is actually a huge area of interest, at least to our transport team at in the center.
So like Hans Metal type, but like this kind of
Yeah. So that's all in game um, uh, within this framework.
I see.
Mhm.
Martin has a question.
Hi, thanks, Ming. Wonderful talk. Thank you so much. I wanted to ask about the hybrid structures again. So you
Mhm,
had talked about the Fermi surfaces, saying that basically we don't see the monolayers in the 1,2,1,2 and the 1,3,1,3 because they're gapped out. But
mhm.
but before that, you also showed sort of the band structures, and made the statement that I think if I understood correctly, it looks sort of just like the sum of the parts.
Right,
I mean,
right, right.
I do see some mixing here, but I mean, is the take-home message that these are sort of, not interesting because the layers are not really coupling and giving you something more than the sum of the parts, or what is the
I
take-home
think so.
message?
That's my basic understanding is that they're effectively decoupled. So, if I just upgrade my level of theory, I still see that same picture. I can imagine if I do the calculation for this 214, I would see this insulating state as well. So if I just take correlated metal, and put them together in this way, I see this superposition, at least at this level. Does that answer your
Okay.
question?
Yeah, perfect. Yeah, thank
Okay.
you.
No.
Ismail?
Yeah, Harry, very nice talk. Just sort of to put you on the spot, I haven't thought too much
Okay.
about the infinite layer square planar series. So all this
Mhm.
discussion about whether single orbital dx square minus y square is
Mhm.
adequate or whether you have to mix other orbitals in. I wonder whether you have your view about that you could share with us.
Um, I think I think right now there's compelling evidence for both. And of course, you can cherry pick what experiments you want to try to match your data to.
Hmm.
I think if you're talking about superconductivity,
Right.
as you probably know, the TU Venn group has a very compelling argument where they can match the dome of both the infinite layer and the finite layers. Um, by just taking some single band model, mapping the problem to a single band Hubbard model, and just solving that within the various approximations that they can afford. But that's just looking at superconductivity. If I want to look at spectra,
Hmm.
there's compelling evidence that you need a multi-orbital picture. Um,
Hmm.
in reality, it's probably some admixture of both, and that's why it's such a interesting case that you need to sort of span two limits at the same time.
Yeah.
Um, so
Okay. Yeah. Thank you.
yeah,
Maybe I can ask the last question. Nobody else. So you mentioned there's additional pocket in your calculation which has this like elliptical shape. Does the
yeah.
have broken symmetry, or what is the reason for this? Maybe I missed this point.
Oh, this sort of center pocket around
Yeah.
the gamma point.
Yeah.
We're just in the when we go to this orthorhombically distorted
Oh,
structure, you get this orthorhombic distortion. But this is just this sort of z squared bonding band popping up around the chemical potential that we can play games with and moving it around depending on what we do. But that's why it looks like that.
understand. Thank you.
Mhm.
With that said, I guess we are thank Harrison very much again for this great talk.